In this playlist, I'm showing you how to build a CPU. If you haven't watched the previous video, check out the link to the playlist. In this video, we'll build a simple circuit that is a lot like the light bulb circuit we discussed in the previous video. In this circuit, we'll use three different components: an LED, a resistor, and a switch. We'll describe what each of these components does later in this video. We'll use a breadboard to build our circuits. A breadboard is a small panel that lets us connect wires and electric components together by plugging them into the panel. The breadboard has lots of holes. We push the leads of components, which are the wires connected to the component, or the ends of jumper wires into these holes, to connect various wires and components together. We notice that the breadboard has two separate halves that seem to mirror each other. If we look at each of these halves from the middle out, we notice that there is a gap in the holes of the breadboard that runs the length of the breadboard. Eventually, we will place components on the breadboard by pushing in the leads of the components so that the components straddle this gap. We notice that the breadboard labels the columns of holes with numbers and the rows with letters. The breadboard connects the holes of the columns together, such that if we insert a lead from a component and a jumper wire in the same column, the lead and the wire will be connected, but only on each side of the center gap. In other words, holes 1A through 1E are connected, and holes 1F through 1J are connected, but holes 1E and 1F are not connected. The same is true for each of the 63 columns. Your breadboard may be shorter, but it works basically the same way.
It's all the same.
We notice that there are also two rows of holes that run along the top of the board, and two rows of holes that run along the bottom. All holes in a single row are connected, but holes in separate rows are not. Even though there are slight gaps in each row at an interval of every 5 holes, the holes on each side of the gap are connected. The gaps just make it a little easier if we need to keep count. We usually use these rows at the top and bottom for our power source connections. As we discussed in the previous video, the power source could be a battery, but I'm going to use a power supply. The power supply I will be using plugs into the wall and converts the alternating current wall electricity into lower voltage direct current. If you want to follow along with these projects, feel free to use either a battery or a power supply. To connect your power source to the breadboard, you will want to place the leads for the power source in separate rows on the outer edge of your breadboard. On most breadboards, these rows have a red line running along one row and a blue or black line running along the other. Your power source also has a positive lead and a negative lead. By convention, red means positive. So connect the positive lead from your power supply to the red row of holes on either the top or bottom of the board. Connect the negative lead to the row with the blue or black line. It is important that you do not connect the positive and negative lead in any way that they have a direct connection. Doing so would create a short circuit. If we short circuit a battery power source, we will run the battery down very quickly. And if we create a short circuit with a power supply, we could damage the power supply. Next, let's place each of the components on the board. Let's start with the LED. The acronym LED stands for light emitting diode. When we run current through an LED, it lights up like a light bulb, but there are a few things to know about LEDs before we try to do this. If you have ever created a simple circuit like that of a flashlight, you know that all you have to do to get the light to turn on is to connect one side of the light bulb to one lead of a battery and the other side of the light bulb to the other side of the battery. While this works for light bulbs, it doesn't quite work this way for LEDs. Diodes are a type of electrical component that lets current flow in only one direction. LEDs are diodes that give off light when current is flowing through them. So if we want the LED to light up, we need to connect them into the circuit correctly. If we look at the LED closely, we notice that the LED has two leads, and that one of the leads comes from a side of the LED that has a flat edge. The lead near the flat side is called the cathode, or the negative lead. The other lead is the anode or the positive lead. Some LEDs do not have a flat side. So how are we to know which side is the cathode and which side is the anode?
Which is which?
In this case, the shorter lead is the cathode and the longer is the anode. Some components like LEDs have a positive side and a negative side. Other components such as light bulbs do not. When a component has a negative side and a positive side, we say that the component has polarity, which just means we need to make sure we connect the positive and negative sides appropriately. Place the LED on the breadboard so that it straddles the center gap. Now, we can connect the cathode side of the LED to the negative lead on the power supply by placing a jumper wire in the same column that contains the LED's cathode, and the other end of the jumper wire to the negative row of the power source. Leave the anode of the LED for now, and we'll come back later and connect it. Next, let's place the resistor on the breadboard, straddling the center gap. Resistors look like tiny hot dogs with a wire sticking out of each end. Unlike LEDs, resistors have no polarity, so it doesn't matter which lead goes on which side. If we look closely at resistors, we notice that they have several stripes of various colors painted around their bodies. The color and the placement of these stripes tell us something about the type of resistor we have. The purpose of a resistor in a circuit is,
Drumroll, please.
strange enough, to increase resistance. Duh! In our LED circuit, we need to increase resistance so that our LED doesn't burn up. If we just use our LED without a resistor in the circuit, too many electrons will pass through the LED too quickly and cause it to get too hot. So, the resistor adds enough resistance to protect the LED. The stripes on the resistor are a color code that indicates how much resistance the resistor will introduce into the circuit as specified in ohms. There are 3, or sometimes 4, stripes on the resistor. Each stripe can be a different color. There are 10 possible colors for each stripe, where each color represents a different digit. Here is the mapping of colors to digits. I'll leave a link in the description to this mapping. The first 2 stripes represent the first 2 digits in the number of ohms, and the third stripe indicates the number of zeros appended to the first 2 digits. So for example, since red maps to the digit 2, 3 red stripes would represent 22 with 2 zeros after it, or 2,200 ohms. A resistor with green, blue, and yellow stripes would represent 5/6, followed by 4 zeros, or 560,000 ohms. Some resistors will have a 4th stripe. In this case, just treat the 3rd stripe as a 3rd digit, and the 4th stripe indicates the number of zeros. There is usually an extra stripe on the other end of the resistor that is either gold or silver. This stripe indicates the tolerance of the resistor. If this stripe is gold, the resistance of the resistor may vary as much as plus or minus 5%. If the stripe is silver, the resistance may vary by as much as plus or minus 10%. The size of the resistor we use to protect the LED ought to be something like a 1,000 ohm resistor. Larger resistance values may cause the LED to be a bit dimmer, but they won't hurt anything. However, if the resistance is too small, we could damage the LED. By the way, instead of spelling out the word ohm, people may use the symbol omega instead, but it means the same thing. Let's recap where we are in our project at this point. We have connected the positive lead of the power source to the breadboard to a red row on the breadboard, and the negative lead is connected to a blue row. We have a jumper wire coming from the blue row of the breadboard to the flat side, or short side, of the LED. We have a resistor straddling the center gap, but we have not yet connected it to anything. At this point, let's connect a jumper wire from the anode of the LED, which is the non-flat side or the longer lead, to one of the sides of the resistor. As we mentioned, the resistor has no polarity, so it doesn't matter which side we choose. Notice that the electrons in our circuit will flow from the negative lead of the power source through the LED and then through the resistor. There is no other path for the electrons to take. When there is only one path through some components, we say that the components are connected in series. The alternative to connecting components in series is to connect them in parallel. When we connect components in parallel, electrons have branches where they may take various paths. We'll discuss more about series versus parallel later. The next step in building our circuit is to connect the switch in series with the rest of the circuit. We can place a push-button switch so that it also straddles the center gap on the breadboard. The switch has leads on two sides. Position the switch over the gap so that the leads that come out of the same side of the switch are on the same side of the gap. If your switch doesn't want to stay in the holes, you can use some needle nose pliers and carefully straighten out the pins. Now, run a jumper wire from the unconnected side of the resistor to one side of the switch. Notice that switches, like resistors, do not have polarity, so it doesn't matter which side we connect the jumper to. Finally, connect a jumper wire from the other lead of the switch. Note that the switch has 4 leads. 2 of the leads are connected to one side of the switch, and the other 2 are connected to the other side of the switch. It really doesn't matter which of the 2 leads you use as long as you get the correct side of the switch. If we manage to get the jumper wire connected correctly to the switch, we're done.
We're done.
If we have connected the circuit correctly, and our power source is supplying power to our circuit, we should be able to push the button and see the LED light up. Should your circuit not operate correctly, here are a few tips to consider. First, stay calm and assure yourself that there is a logical explanation. We may have a tendency to become very anxious when things don't seem to work.
Anxiety, depression.
And we are working with unfamiliar technologies. But realize that the technology is not magic. It's logical, and you can reason your way through the problem.
It's logical.
Now, systematically, work through the circuit, looking at each connection. For each of these connections, make sure the connection is secure and that the connection is correct. Pay special attention to the polarity of the power source and the LED. If you have carefully verified the entire circuit this way, there is a high probability that your switch is not connected correctly. A symptom of the switch being connected incorrectly is that the LED either stays on all the time or stays off all the time.
On or off!
Another possible problem that can cause a non-working circuit is if the LED polarity is incorrect. Check to make sure you connected the anode and cathode as previously described. Finally, the only other likely problem might be that you accidentally connected the LED directly to power without having a resistor in series, in which case it is possible that you damaged the LED. Try using a different LED to make sure this is not the issue. Sometimes pictures we're showing in this video are somewhat imprecise, especially if all we want to extract from the image is how to connect the components.
Oh, and you better start reading the instructions because you're going to be using it in about 5 minutes.
At the same time, some sort of picture seems much easier to understand than an English description. What we would like is something like a picture, but more precise. Circuit designers have come up with just such a mechanism. They call them schematics. A schematic is a symbolic representation of a circuit that is intuitive like a picture, but a bit more precise. In schematics, we represent components with specific symbols and connections with lines. Here is a schematic for the circuit we just built. Starting on the left side of the schematic, we see the symbol for the power source. In this case, the power source is a battery. The schematic symbol indicates the polarity of the battery with the plus sign at the top and the minus sign at the bottom of the symbol. If we follow the line from the negative lead of the battery, we find that it connects to the symbol that looks like a triangle with a line under it. This symbol is the LED symbol. We can see the arrows pointing away from the triangle, indicating the LED emits light.
You can see light! Can you see the light?
The schematic indicates the polarity of the LED with an A to indicate the anode and AK to indicate the cathode. Yeah, we realize cathode is not spelled with a K, but this is the convention. As we move counterclockwise from the LED, we see the jagged symbol that represents the resistor. Note that the schematic indicates that this is a 1000 ohm resistor. Finally, just to the left of the resistor is a symbol for a switch. The two terminals of the switch are not connected by the diagonal line, indicating that the switch is open, meaning that the circuit will not be complete until we push the button. At this point, we have built our first real circuit. You may be wondering what any of this has to do with how a CPU works. To answer this, we need to understand the notion of an analog. An analog is a model of something that has behaviors that are similar to the thing that is being modeled. Computers rely on digital and Boolean logic, so what we want to do is to create an analog of simple Boolean functions. The simplest Boolean function is the identity function. Functions have inputs and outputs. The identity function has one Boolean value as input and a single Boolean value output. By definition, the output of the identity function is the same as its input.
Seems fairly obvious.
If we think of the switch as the input, we're pushing the switch maps to true and releasing the switch maps to false. And if we think of the LED as the output, where when the light is on represents true and when the light is off represents false, we begin to understand how this circuit models the identity function. When we push the switch representing an input of true, we see the LED light up representing an output of true, and vice versa. This isn't really as lame as it may seem at first.
Why isn't it lame?
Because we'll do it in a way that won't be lame.
The idea of being able to model Boolean functions with circuitry is a critical leap for learning to construct a computer. So there we have it. We are now armed with enough foundational understanding to start to build more sophisticated circuits that can do more things. In the next video, we will build circuits to represent more sophisticated Boolean functions. Then, with these functions, we will be in a position to begin building computational mechanisms.
Technology's too sophisticated.
Be sure to subscribe and click the notification bell so you can be notified of future videos.